go through it because I want you to make sure you're better with it, because this is what's on the midterm. So we have to get it better. Some of you did great, but enough didn't that I want to make sure that we get it there. Okay.
I just hope that
All right, guys. This is our hepatic clearance celebration, and some of you are celebrating and some of you are probably sad. Remember, this is an extra quiz, so we can drop this one if it's your lowest, but let's learn from it, okay? Because this is the kind of stuff that's going to be on your exam. So please ask your questions, pay attention. Hard to, right? I'm ready for break too, man. Okay. So hepatic clearance, let's do it. All right, first question. If your patient was a slow metabolizer, have you guys talked about slow metabolizers at all in pharmacology? No. Anyway, you can be genetically a slow metabolizer of CYP2D6, which is one of the enzyme systems. So what this means is that these people have a lower intrinsic clearance than others. Okay, so what's happened here is a decrease in intrinsic clearance. What changes would you expect to need to make in their dosing regimen of drug R? So drug R is totally cleared by the liver. We know that because this FE, what does FE mean again? It actually stands for the fraction excreted unchanged in the urine, but it's basically the percentage that is due to renal clearance. So these are both hepatically clear. FE stands for the fraction of drug excreted unchanged in the urine. So it's the fraction of drug you can find in the urine that's still the parent drug that you gave in the urine. That means it's been cleared by the kidneys. It hasn't been changed by the liver, hasn't been metabolized. It's just totally cleared by the kidneys. Okay, so if FE is 1, it's totally cleared by the kidneys. If FE is 0, it's totally cleared by the liver. If FE is 0.75, then it's 75% cleared by the kidneys, 25% cleared by the liver. Okay, got that? Okay, what changes would you expect to need to make? Okay, so the first thing we're going to ask about, do we need to make a change in dose rate? Well, how do we decide? Well, we want to look at CSS average, right? And CSS average, we know, and it's being given PO, so we have to think about bioavailability, dose rate, and clearance. Do we need to look at CSS free to decide this? Not in this case. Why? Because there's not been a binding change, right? As long as there's no binding change, we don't have to look at free. We should get the same answer. Yes, Chimaka. We can look at the total. Okay, good. So what we need to know then is what determines clearance, right? Since we know it's hepatically cleared, we're hoping it can either be considered a low E or a high E drug. How do we decide if drug R, so this drug here, is a low E or high E drug? Yeah, Chamaka. That's it, girl. That's right. So we know that, I think some people didn't know this. Hepatic clearance is equal to Q times E. We need to figure out E. We know that the clearance for this drug is 3 liters per hour. And if we assume a normal Q of 90 liters per hour, what's our E going to be? I wouldn't even do the math. It's low, right? Small. It's a low E drug. Therefore, clearance is equal to intrinsic clearance times fraction unbound, right? And FH is approximated by 1. So we don't have to worry about a root difference, do we? There's no root dependence here. But what we're going to want to do is say, okay, so CSS average is equal to FA times FG times FH, which is 1 in this case, times dose rate, all over clearance, which is intrinsic clearance, times fraction unbound. So now we did all that, but what's happened? There's been a decrease in intrinsic clearance, therefore a decrease in clearance, therefore there's going to be an increase in CSS average. So what do we want to do? Decrease dose rate in this patient, right? Decrease dose rate. They're slow metabolizers. They're going to have a slower clearance. Therefore, there's going to be an increase in their total concentration and free concentration at steady state. Therefore, we're going to want to decrease the dose rate. You all good with that? So we're going to decrease dose rate. How about dose interval? I'm going to erase this so we have a little bit of room. Did everybody understand how we got the E and that we got to a low E? Okay. So now, in order to figure out if we want to change the tau, we're going to have to look at, we'll look at half-life. Is everybody okay with looking at half-life? So we're going to say 0.693 volume over clearance. We figured out it's a low E drug, so clearance is going to be determined by intrinsic clearance times fraction unbound. The volume of distribution, remember, is all about binding, isn't it? What's happened again? We've had a decrease in intrinsic clearance. Therefore, we're going to see a longer half-life because the clearance has decreased, hasn't it? So we're going to want to take advantage of that and increase the tau. So we're going to decrease dose rate, increase tau. Oops, do you want me to leave that? I'm recording this too, so you should be able to get this later if you want to go through it. Oh, yeah. We're decreasing dose rate, but we're not decreasing dose interval. Decreasing dose rate and increasing dose interval. There's the answer. This is ridiculous, isn't it? See why I have you write it in instead of, because this will make your eyes cross. Well, sorry, I don't have too many questions like that. Well, it's the same question, but I have you write it in, so it's a little easier to manage. All right, your patient is on drug R. Drug R is a new drug R. That's annoying, isn't it? No. Wait. Yeah, drug R is different here. Oh, okay. New drug R and has an exacerbation of their heart failure, therefore a decrease in Q. So this is what we're really looking at here is a decrease in Q. How will you change the dosing regimen to compensate? I would suggest, okay, so we need to figure out again, first of all, it's a change in Q. It's not a change in binding. Therefore, we can look at total, right? So we're going to look at total concentration at steady state. Doesn't say where it's given IV or PO, or does it? I might have to. Oh, wait, here, PO. There it is, PO. FA times FG times FH times dose rate, God bless you, all over clearance. So we need to figure out what kind of drug this is. So here we're going to look at our clearance So, and again, these are all cleared by the liver. So the hepatic clearance is 1,300 mils per minute is equal to Q times E. We need to figure out E, and we know Q is 90 liters per hour or 1,500 mils per minute. So what's our E? It's not small this time, I don't think. It's high. E is 0.87. So that's a high extraction drug. Dun, 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 dun. So then we know that clearance is approximated by Q, and the dreaded FH is Q, God bless you, over intrinsic clearance times fraction unbound. All right. Is everybody good with this so far? A little more room to write. Okay, so our total concentration is steady state. Oh, what did I do there? Okay, won't do that again. So as FA times FG times FH, which is Q over intrinsic clearance times that weird fraction unbound that the liver sees as 1, all over clearance, which in this case is Q. You know what? I'm going to do it down here because that's too crazy. FA times FG times FH, which is Q over intrinsic clearance times that fraction unbound that the liver sees as 1 because of non-restrictive clearance times dose rate, all over clearance, which for this drug is determined by liver blood flow. Notice those Q's cancel, don't they? And what's happened here is a decrease in liver blood flow. So yes, decrease in liver blood flow will decrease the fraction that makes it through the liver. It also will decrease the clearance to the same extent. And so at steady state, there will be no change in your CSS total. Therefore, no change in dose rate. Okay. And what about dose interval? If we look at half-life, we're going to say 0.693 volume, which is determined by binding. There's no change in binding that we know of. But clearance is approximated by Q, isn't it? What's happened here? There's been a decrease in Q. So our half-life is going to go up due to that change in clearance. So no change in dose rate, but we want to increase our tau because we follow that half-life, right? That's a tough one. Questions? Yeah. FA times F, this one here. That, wait, where? It's a lot of scribbling, I know, I'm sorry. Down here? So this is an F, this is an FA. This is an FG. And this is FH for a high extraction drug. So it's Q over intrinsic clearance times that funny fraction unbound that we kind of look at as 1 times dose rate all over Q. Is that what your question was? No. Which one?
The half-life, the one next.
Oh, okay. 0.693. Volume of tissue, there should be a T, but it looks like a 7, but it should be a T times fraction unbound in plasma over fraction unbound in tissue divided by Q. Okay, so the only thing that's changing here is that Q, which is that decrease in clearance caused by the decrease in liver blood flow. Okay? Other questions? Okay, now your patient is on drug S and has an increase in cardiac output. So now we've got an increase in Q. How will you change the dosing regimen to compensate? All right, let's look at drug S. Well, 4 liters per hour, is this a high or a low extraction drug? Low, right? Is everybody okay with me making that leap? Remember, clearance is equal to Q times E. So if our clearance is 4 liters per hour and our blood flow is 90 liters per hour, our E is going to be very small, 4 divided by 90, whatever that is. So it's a low E drug. Is everybody good with that? And how we decided it? So we already know this is a high E drug. This is a low E drug. We can tell by looking at this guy, this is a high E drug too. Isn't it? So these are both high first pass drugs. Okay, but now we're doing with low E, we make a little bit of a happy dance. So clearance is approximated by intrinsic clearance times fraction unbound. And our FH is approximated by 1. There's no root dependence here, right? Just to be clear on this other one, if this were given IV, it would be a different story, wouldn't it? That's where we get our root dependence. Oops. All right. And so now this guy is also being given orally. So how are you going to change the dosing regimen to compensate? So what are we going to look at? We're going to look at CSS total is equal to FA times FG times FH, which is 1 for this drug, times dose rate, all over clearance, which is intrinsic clearance, times fraction unbound. So if there's an increase in liver blood flow, is this going to alter our total concentration at steady state? Is Q a determinant of our total concentration at steady state? Do you see Q there at all? So Q should not, this change in Q should not matter because it's a low extraction drug. What's the rate limiting step? It's the enzyme activity and binding, not the blood flow. So the blood flow changing doesn't really matter. Now, am I making a mistake by looking at total rather than free? Am I safe looking at total? Yes. Why? Because there's no binding change. As long as there's no binding change, we can look at total, right? So we're going to say no change in dose rate. How about dose interval? Well, dose interval, we're going to look at half-life. Half-life is 0.693 over volume. There's been no binding change, so there's going to be no change in volume. And our clearance is dependent upon intrinsic clearance times fraction unbound. Has there been a change in anything that determines half-life? Does Q make a change in half-life for this drug? Change in Q? No. So there's no change in dose rate or dose interval here. Okay? Number 4, your patient's on drug S. We already know it's a low E drug, don't we? So clearance will be approximated by intrinsic clearance times fraction unbound, and there's no route dependence because FH is approximated by 1. Now we're given a CYP2C9 inducer. So what is that going to tell you? What's going to happen? There's an increase in intrinsic clearance, right? Everybody understand that that's what that meant? Do you know? A CYP inducer. So we've induced the enzymes that are in the CYP system that clear this drug. Okay? You good, Bo? So we've got an increase in intrinsic clearance. How will you change the dosing regimen to compensate? Okay, this is getting repetitive, isn't it? And there's no room on this slide. Does this allow me? Okay, oops. Okay. All right, so we have a low extraction drug with an inducer, right? So we've got an increase in intrinsic clearance. Was it an inducer? I already forgot. I think it was 2C9 inducer. So what's gonna happen? Can we look at total? Are we safe looking at total, everybody? Yeah, because there's been no change in binding, okay? And this has been given orally, so FA times FG times FH, which is approximated by 1 because it's a low E drug, times dose rate all over clearance, which again, for a low E drug is intrinsic clearance times fraction unbound. So if we've induced these enzymes that clear this drug, this low E drug, we're going to see an increase in clearance, aren't we? Which is going to decrease our total concentration at steady state. Therefore, we're going to want to give more drug, aren't we? What about dose interval? How big of pieces do we want to chop this thing into? Well, we need to think about volume. None of this has changed that we know of. Over clearance. And again, we know we have given an inducer, so our intrinsic clearance will increase, our clearance will increase, and therefore we're going to see a decrease in half-life, so we're going to want to decrease tau. Is this starting to make some sense? Good? Okay. Now your patient's on drug R. Remember, drug R is that high E drug. So it's a high E drug. And it's being given orally. We need to pay attention to the route because it's a high E drug and there's route dependence here, isn't there? Route dependence. So our clearance is going to be approximated by blood flow. Our fraction that escapes the first pass effect is going to be determined by Q times intrinsic clearance times that funny fraction unbound that becomes 1 because of it's going to be usually non-restrictive. So now we're on this high extraction drug and fluconazole, which is a CYP inhibitor. What does that tell us? What's happening here now? That's it. A decrease in intrinsic clearance, right? A decrease in enzyme activity. But now we're dealing with a high E drug. Okay, so we're a high E drug given orally. Okay, what are we going to do? Okay, so a high E drug. So clearance is approximated by Q. Fraction that escapes that first pass effect is determined by Q times intrinsic clearance times that funny fraction unbound. And what's happened here, we've given a CYP inhibitor. So we're seeing a decrease in intrinsic clearance, right? So CSS total, can we look at total? Yes. Starting to think I'm dim now, right? That I ask that every time, but you should ask yourself that every time. And then you can go ahead with total instead of worrying about the free concentration, unless I ask you about the free concentration. So we have FA times FG times FH, which for this drug is Q over intrinsic clearance times fraction unbound, all over clearance, which is determined by Q. Those Q's will cancel, but what's happened here is a decrease in intrinsic clearance. That decrease in intrinsic clearance in the liver is going to allow more of this drug to get through that and be more bioavailable, right? If I was trickier, I would have said, why is this true? Why is CSS average going up? It's because it's an increase in bioavailability. Not because of a change in clearance, but because of the bioavailability. So you're going to see an increase in CSS total, therefore you're going to want to decrease your dose rate, right? What about dose interval? and none of that's changed. Our clearance is determined by Q. Will there be a change in half-life? With a decrease in intrinsic clearance. What's happened is we've given an enzyme inhibitor. Will that affect either volume or clearance in this case? No, so no change. So we're gonna decrease the dose rate, no change in dose interval. Yeah, go ahead.
Because this is high blood flow,
Mm-hmm.
vice versa. Does that not affect this though? Because the Q's on the bottom over time would have being affected.
Well, clearance isn't being affected because there's no change in Q. The reason that there's a change in your total is not because of a clearance change, is it, Ben? That's why I leave this in the numerator so you can see that it's a bioavailability change, not a clearance change. Does that help? Ready to move on? All right, your patient is on drug J. Okay, so this is a new one, still cleared by the liver. Highly bound to AAG. Clearance is 12.7 liters per hour, high or low E? Low E. Everybody good with that? Not even doing the math anymore. It's a low E given orally. All right, this is a high EC. This has, look at the difference in bioavailabilities here. Because we know a high E drug has a high first pass effect, doesn't it? Look, this is only 9% bioavailable. This one's 85% bioavailable. So that's kind of a clue that this is a low E and this is a high E too, isn't it? Anyway, I digress. So drug J has an increase in AAG. Oh, we finally got to a binding change. Dun, 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 dun. So if there's an increase in AAG due to surgery, what does that tell us? What's happening with binding? What's happening to our fraction unbound? It goes down because there's more binding, because there's more AAG, right? Being thrown out. There's been an increase in AAG. So the drug is more highly bound to that protein, isn't it? Which means it's less fraction unbound. So we have a decrease in fraction unbound. So that's what's happening here. So do we need to change the dosing regimen to compensate for this change? All right, so we've got a low E drug given orally where there's a decrease in fraction unbound. Okay, decrease in fraction unbound, low E, PO. What's gonna happen? All right, so we know that clearance is approximated by intrinsic clearance times fraction unbound, and your fraction that escapes the first pass effect is approximated by 1. So let's can I use total to determine what we want to do? Finally, you're going to say no, we can't use total, can we? Because why? There's been a binding change. So do you want to just skip to free, or do you want to know what's happening with total too? We'll skip to free. So we've got FA times FG times FH, which is approximated by 1 in this case, times dose rate, all over clearance, which is approximated by intrinsic clearance times fraction unbound. And then we multiply this whole thing times fraction unbound to get free, right? What do you right away notice because you're all math wizards and wizardettes? Is a female wizard a wizard? Which sounds kind of negative. Witches are a female wizard? Okay. Warlock. Yeah, so maybe not. Wizards. Okay, we'll have to worry about that another day. We'll research it, okay? Wizardess, wizards. All right. So you're all fabulous math folks. So we know that these will cancel, right? So when there's a decrease in the fraction unbound, more is bound, is that gonna change our free concentration at steady state? No, therefore, we're gonna say no change in dose rate, aren't we? How about dose interval? Well, if we look at half-life, again, we have to look at our volume, which is dictated by binding, isn't it? So we see our fraction unbound there again. And our clearance, which in this case is intrinsic clearance times fraction unbound. Those two will cancel. And if there's a binding change, do we expect to see a change in half-life? Tricky. Now, if you made a mistake and didn't consider, oops, I still want that. Oh, shoot, it's gone. Oh, well. How do I go back now? Okay. If you made a mistake and looked at total concentration will be FA times FG times FH, which is 1 for this drug, times dose rate all over clearance. So if you saw this decrease in fraction unbound, knowing that clearance is going to decrease, you might have said to decrease the dose rate, which it would have been correct if you looked at the total. But we don't want to know really what's happening with total. We really want to know what's happening with free. And we know we can't trust total when there's a binding change, right? I might have tripped you up. All right, drug J. Drug J here, let's look at it quickly. This means it's totally cleared by the liver. It's highly bound to AAG. It's a low E drug given orally. So does this drug exhibit restrictive or non-restrictive? Well, since it's a low E, we know it's restrictive, right? Because there's not that great power. It's restrictively cleared. Only free drug can be eliminated, can interact with the enzyme. So we know then that E is going to be limited by the fraction unbound, right? We can also determine the E here. So if we say 12.7 divided by 90, the E is 0.14. And how much is free? 20% is free and we're extracting 14. So we are restricted to only free drug here, aren't we? Our E is less than or equal to the fraction that's free. So because E is less than or equal to the fraction unbound in plasma. I don't know what that's a typo, sorry. Okay? Everybody okay with this? If it were a high E drug, we would expect that it's non-restrictively cleared, right? And can pull that drug, the protein no longer protects it. All right, your patient is on drug S. As I remember, drug S is low E. Sure enough, it's a low E drug given orally, which is a PGP substrate. What does that mean? What's PGP? This forces you to go back and remember like week number 3, where we talked about what? Bioavailability. So PGP affects our FG, doesn't it? Our fraction that escapes the gut metabolism. This may have thrown you into a little bit of a loop because it's not about hepatic clearance. It's about, I want to make sure that you don't get mixed up. So PGP is that efflux pump, right, in the gut wall. So a drug is added that blocks the P-glycoprotein in the gut. So if we think about, if we think about here's our small intestine. The drug is coming down the small intestine. It gets absorbed into the gut wall, right? So that's your FA getting absorbed into the gut wall. And we know we have little enzyme in here, which I think of little Pac-Man here. Here's our little Pac-Man waiting to metabolize the drug. We also have P-glycoprotein ready to throw it back into the gut lumen, right? So if we inhibit those, isn't that what happened? We had a PGP inhibitor. So if we inhibit these, what's going to happen? We're going to have an increase in FG, aren't we? You remember that? So we're going to have, in this case, we've got an increase in FG. How will you change the dosing regimen to compensate? Okay, so this is a low E drug given orally where we have an increase in FG. So if we look, can we look at total in this case? Is binding changed? And we had a change in our fraction unbound, and has there been a change in AAG or a change in albumin or a competing drug? No. So there's not been a change, so we can use total, can't we? FA times FG times FH, which in this case is approximated by 1, times dose rate all over clearance, which is determined by fraction unbound and intrinsic clearance. And what's happened? There's been an increase in FG. Therefore, an increase in CSS total. Therefore, we're going to want to decrease our dose rate, aren't we? We've improved the bioavailability. And if there's a change in bioavailability, will there be a change in half-life? Will we need to make a change in dose rate? Is bioavailability part of what determines half-life and K? No. Remember, it's 0.693 volume over clearance. Bioavailability isn't a thing here. We could write this all out. If that makes you happy. Will a change in FG affect half-life? In this case? Nope. So no change in tau. Okie dokie. All right, we have true and false left. So drugs with an FE of 0, again, that means it's hepatically cleared, right? No renal clearance. That are low E drugs. Okay, that means that clearance is approximated by this. And the fraction that gets through the liver is 100%. About. Always have a relatively large F. Well, this is true. They always have an FH approximated by 1, but will they always have a large F? Aren't there other components to F? We know FH will be 1, but do we know anything about those two? Does knowing that it's a low E drug tell you anything about FA, if it's going to be absorbed, or if it's going to be subject to P-glycoprotein or the enzymes in the gut wall? No, it has nothing to do with, we don't know. It could be high E, but since we don't know about these two, we can't say that that's true, so we have to say false. This is an important point because I don't want you to think if a drug has a low bioavailability that it's definitely a high E drug. That isn't true because we don't know what's going on with these, right? Remember, some of the drugs we looked at had just very low FGs or very low FAs. So all it tells us about is this component, which is only one component, right? You okay with that? Total, oh, everyone should have gotten this one. Total concentrations at steady state can be used to determine what is happening with free concentrations at steady state as long as the plasma protein binding has not changed. How many times have we said that, right? That's true. Okay? Do you feel better about these concepts after going through this? These are the kinds of questions I'll be asking on the midterm on hepatic clearance, okay? Tomorrow, I want to just, I'm already like too much time. Let me just, well, we have about 5 minutes. Let's just start renal clearance. Did I open up renal clearance, Olivia? No? Okay, but I did release it. Thought I did, but you know, I'm getting kind of queasy. Wait, I want renal. I'm gonna just start with just basic overview of hepatic clearance. Because I want to have as much time as we can tomorrow to get into some problems, so. Okay. Total body clearance, or CT, we usually think of as the sum of our renal and hepatic clearance. And the fraction excreted unchanged in the urine, as we've been talking about, FE, is really the percentage of clearance due to renal clearance. So you can always determine renal clearance by multiplying FE times the total body clearance. So FE times the total body clearance will give you renal clearance. Okay. I don't want you to worry about this too much, but renal blood flow is about 20 to 25% of your cardiac output, which is 1.2 to 1.5 liters per minute. We use 1.5 liters per minute as our cardiac output, and the liver blood flow. Renal plasma flow is your renal blood flow adjusted for your hematocrit. Don't worry about that too much. Glomerular filtration rate. Have you guys talked about GFR at all? And you probably did in anatomy, maybe in physiology. The GFR, glomerular filtration rate, which is hard to say 3 times fast, glomerular filtration rate, which we call GFR because of that, is 10% of your renal blood flow. So about 10% of it, or 125 to 50 mils per minute, gets shunted to your kidneys. So this is what goes into the glomerulus, which you know is like a filter that then goes into each of the tubules that make up your kidneys, your kidneys. There's 3 processes that happen in the kidney. So as the blood flow comes into the glomerulus, which I'm expertly drawing here as like a filter, like a bunch of blood vessels, it then enters the nephron. So this is now the nephron. So the glomerulus is the entryway of the blood. So this is blood coming into the glomerulus. And then it enters the nephron. Then so I will tell you, only free drug makes it through this glomerulus. If it's bound to a protein, this is like a filter. So if it's bound to a protein, once again, it's too big to fit through the glomerulus. This is a protection for your body. Do you think that you want to be peeing out proteins all the time? That's right. Why not? They're really hard to make. It takes a lot of resources to make a protein. You want to save those proteins. So that's one thing. If you have protein in your urine, you know that's a bad thing, right? That means your glomerulus isn't doing its job. Okay? So only free drug makes it through the glomerulus. So if the drug is free, it now makes it through the glomerulus. It's now in what's called the proximal tubule. Proximal because it's closer to the body. Distal is on its way out. Okay, do you remember those terms from A&P? Proximal, close; distal, far away. Kind of makes sense. Distal, distant. Okay, in the proximal tubule, first we've got what's called filtration. Then in the proximal tubule, we have carrier systems that will move drug from the blood. So there's blood vessels all around this tubule. We'll move from the blood into the nephron, which is where the urine is being made, right? So this is urine. and this is blood. We have carriers that will move drug from the blood into the urine. That's called active secretion. Notice the word active. Active secretion. Guess what active means? This is Michaelis Menten. There's carrier systems that you can overwhelm. We'll talk more about this tomorrow, but we have active secretion. And then as you move down the nephron, we have big time water reabsorption going on. Water being, so everything's being dehydrated in the nephron. Why do you think that happens? Remember, our GFR coming in here is what? 125 to 150 mils per minute. What if you didn't reabsorb any of that water? Let's just say we wouldn't be sitting in here for class, would we? If you're making 150 mils per minute of urine, and you would be dehydrated all the time, right? So you would have to have an IV and be sitting with a leg bag to sit in class, right? Because you would need to have water replenishment all the time, and you would be peeing all the time. So yay for water reabsorption in the kidneys, right? So what's happening to the drug that's in this nephron as it moves down to the distal part of the tubule? It's getting more and more concentrated, isn't it? The last thing that happens is we have passive, listen to the word passive. This is active secretion. This is active. Then at the distal end of the tubule, we have passive reabsorption of drug. And it just follows, again, just passive concentration dependent diffusion. Whether or not the drug is reabsorbed or not just follows the rules of having a concentration gradient that powers it. Yes. So. Well, the loop of Henle is somewhere in here, but this is oversimplified nephron. But the loop of Henle is part of this. But the drug action happens at the glomerulus, the proximal tubule where there's active secretion, and then finally in the distal tubule, there's passive reabsorption. So there's two processes that remove drug from the body and put it into the urine. That's filtration, and only free drug gets in through filtration. But then even if it's not free, it can be actively secreted into the urine. So active secretion, which happens in the proximal tubule. This happens at the glomerulus. And then last but not least, there's a chance for drug to be returned to the body through passive reabsorption before it goes out into the bladder and then out of the body. Okay, so here's my little picture of that. So here's renal plasma flow into the glomerulus where we have filtration, only free drug. Then it goes in. So now we're in the urine, in the nephron, right? The proximal tubule, we have active secretion. So drug is being added from the blood into the urine. And then we have all this water reabsorption, big time water reabsorption and drug reabsorption in the distal tubule and out in the bladder. All right, then we'll pick up from there tomorrow, okay? Thanks, guys.